Okay, so my name is Miguel Branco. I'm a researcher at the database group at EPFL, and I want to talk about a system we're building called RAW. So what is RAW? So RAW is a database that queries files, that answers queries directly over files, and what we call in situ. So why do we do that? Well, simple reason. There's plenty of files around, and they tend to host pretty important data. And why do people store data in files and not in databases? Well, we heard some of the reasons today. Sometimes the data is just complex. It's just not a good fit for tables. Issues of ownership, issues of vendor lock-in, long-term preservation, etc., etc. So those are some of the reasons. So how did we go about building RAW, a database over files? So we started from a clean slate. We had a set of goals. First, we didn't want to have an ETL phase. So the idea that we look at ETL and we think of it as a first phase in using a database system, not as a separate thing you'd want to decide as a second-class citizen. We wanted a declarative query language, SQL-like. We wanted to have some ability to handle some more complex data, tables, of course, then arrays, hierarchies, etc. We need the system to be flexible enough so that if you have, multiple file formats, whether it's CSV, Excel, or an existing database system, or some custom binary format that we could bring it in. And we didn't want things like, static schemas and all the like being defined in advance and being very strict. And of course, for this thing to be useful in practice, we wanted it to, it had to be efficient. So how do we do that? Well, I don't have much time to go into the detail, but about the discussion we had just before, the relational algebra is just not a great fit for some of the queries that we see out there, because we do get access to some of the queries that people are using over files. So we use something which is not relational, but it's just very similar to relational. It's just a bit more expressive to handle hierarchies and recursion and a few other things. How we do it in practice, it uses most of the technology you're used to in a modern database system, column stores, vectorization. There's some new details. For instance, positional maps, which are sort of indexes that index the structure of data, not data itself. So it turns out we need those things when we are trying to query files directly and to make it efficient. And then we make also heavy use of code generation techniques. So if you have a query that goes over a binary format that you just custom made, we actually code generate the query and the access to the file in the same step. Everything is tightly coupled together, and that makes it very efficient. And of course, the whole system was designed for late schema definitions, lazy schema definitions. So if you change the way you reinterpret your raw data, that turns out to be very easy, and not having to rebuild the whole thing. So we do have a prototype running. It builds most of these pieces together, puts them together, and since we're in Switzerland, we have CERN next door, and that was a pretty challenging use case. So we went in and took some of their data with their permission, some of the root physics data that Dirk was just describing. We took 2 of their queries just to find the Higgs candidates from Atlas. And these were just very complex C++ files that took forever to understand what they were doing, because the whole thing is bound together, the data access and the querying, etc. We tried to dig out the declarative part from that and implement it in our system, and it turns out it worked, and that's how we found many of the details on the limitations of the traditional relational approach to this. And it works out well, and you see the performance numbers there. This is 900 gigabytes run over 900 gigabytes of data, so not a lot of data. But it does prove the principle. And comparing the existing system, which takes a certain amount of time, with our system, if the system is cold, it takes pretty much the same time. If the system is warm, our prototype is just over 2 orders of magnitude faster. And the reason is that we just use what databases do, right? Vectorization, column stores, and etc. And we build indexes, and the whole thing just works very, very well together. So, since I don't have time to go through everything, you can just find me in the poster session. We are doing some interesting things with SciDB, coupling with SciDB. We are also doing it with PostgreSQL. And again, if you want to learn more about the system, just come and find me at the poster session. Thank you.